Hey everybody, it's Ripley back again. I hope you're all doing quite well. We're going to talk about trigonometric substitution, and if by the end of this lesson I don't hear a which would be the sound of your mind being blown, you're just not paying attention. This is a crazy section. It's probably the craziest of all the techniques of integration. And I'm going to start it with what appears to be just a lowly little easy integral. I'm going to take the square root of 4 minus x squared, the antiderivative of that dx. Now, you may say, Ripley, what? I don't see a trig value anywhere near this thing, all right? Why are you talking about trigonometric substitutions? Well, I'm going to show you something really quickly here, all right? I'm just going to write some stuff up. Let's talk about the ways in which we can write our trig identities. Do you agree that we can write, the biggies are sine squared x plus cos squared x is equal to 1, right? We also know that if I divide through everything by cos squared, that I know that tan squared x plus 1 is equal to secant squared x. Now you may say, wait, what are you doing over here, Ripley? Something looks a little crazy. Well, that's because if you look really closely at, say, this guy, I can rewrite this as sine squared of x is equal to 1 minus cosine squared of x, or I can write it as cosine squared x is equal to 1 minus sine squared of x, right? I can write it either way. Now, if you look really, really closely at this, you might notice sort of a parallel here, right? You might notice that like something's going on. What is it? I got a 4. Well, that's a 1. But I might be doing something funky. I might want to substitute something in, introduce a new variable to get this thing in. But we're getting a little ahead of ourselves. First things first, let's think about what this really is. This is the indefinite integral of the top half of a circle of radius 2, is it not? So if I were to take a circle of radius 2, and I were, that's a pretty good circle. And I wanted to find the area of the top half. Well, that's easy, right? That's just the top half, right? The semicircle of radius 2. Well, pi r squared is going to be 4 pi, and I divide that by 2, and I get 2 pi. This guy would be pi. But what if I wanted to integrate from, say, I don't know, let's call it 0.5 to 1.5? Well, now I don't have those geometric constructs anymore, do I? I'm stuck. Like, I don't know how to do that. Well, let's play a little bit. Let's just see what happens. I'm going to propose some stuff, and it's going to blow your mind at first, but don't panic. But just follow along. And remember, I'm still following the rules of substitution. But wait, I'm getting ahead of myself. Why do I need to introduce new techniques? Let's go through our punch list. First and foremost, is this an antiderivative? Is this a function whose antiderivative I've memorized? The answer to that would be a big fat no. Is there a u substitution? Well, not one that's spitting itself out. I mean, my first instinct would be to let what, u equal 4 minus x squared, but then I end up with a negative 2x, and I got nowhere to go with that, right? Can I do parts? Well, I suppose I could, but then I'd have to let u be this guy, and then the derivative of, oh, good Lord, the derivative would be awful. It'd be negative x over root 4 minus x squared. If you do that in your head, it's pretty easy. What about a trig sub? Well, or a trigonometric integration like we did in the last section. That's not going to work. Or if you're not using our textbook, you did somewhere along the line. That's not going to work. So we have to introduce a new technique. That technique is called trigonometric substitution. Now, just watch what I do for a sec, all right? And then we'll talk about why I was able to do what I was able to do and how we can extend that into different situations, okay? I am going to let x equal something now. Notice this is not a u substitution. All right, I'm not using a u substitution to sort of parse out a piece of this integrand. I'm introducing an entirely new form to this integrand. And that form is going to be, I'm going to let x equal 2 sine of theta. I can't let it be 2 sine x because that doesn't make any sense. All right, I need these things to be the same thing always. Whenever I see an x, I can put a 2 sine of theta in. Now, let's change colors and let's try and figure out why I did that for just one sec. Let's make it obnoxious. I guess purple's not too bad. When I do that, let's watch what happens. This becomes the integral of 4 minus 4 sine squared theta, doesn't it? All right, now there's going to be a whole bunch of other stuff over here, but let's just look at this and see what that becomes. Because there's going to be some other stuff, because clearly we have to account for the dx and all that other good stuff, don't we? All right, well, I can factor out the 4, and the square root of 4 is 2. So I could pull a 2 out, and this becomes the integral of the square root of 1 minus sine squared x, or excuse me, sine squared theta, doesn't it? And there's a whole bunch of other stuff. This is already looking helpful. Now watch what happens. 2 integral, hey, wait a sec, 1 minus sine squared, 1 minus sine cosquared. The square root of cosquared is just hey, something special just happened. Well, let me change my color back to black, and let's actually go through the process. Remember, I'm allowed to do what I'm doing because I can substitute anything I want as long as I account for all the parts of the integrand. If x is 2 sine theta, then dx is going to be 2 cosine of theta, d theta, right? Because this would be dx over d theta, and I can algebraically deconstruct that. So let's see what happens. Well, this becomes, now we're going to go nice and slow. This becomes the integral of the square root, I'm going to write it up. This becomes the integral of the square root of 4 minus 4 sine squared theta times 2 cosine of theta d theta. That's this other garbage that I was talking about. Now, we already showed that this turns into this, turns into this. So the whole thing, if you notice, just turns into, well, I picked up a 2 cos theta here, and I pick up a 2 cos theta here, so this becomes the integral of 4 cos squared theta d theta. Whoa, that was crazy. Well, let's play a little bit more. If you recall from trig, let's call it trig, that what will this turn into? Well, cos squared is 1 plus cos 2 theta over 2. The 2 will cancel with the 4 to make another 2. So this should be the integral of 2 minus 2 cos 2 theta, right? D theta, right? 4 times 1 plus, wait, where did I get a minus from? That should be a plus. Plus cos 2 theta over 2, right? This goes into this, I get a 2, and out pops this. So this turns into 2 theta plus, now look close. When I take the antiderivative of that, that's a linear term, so it's going to pop out and divide, right? The slope divides. So this is going to be what? Plus sine of 2 theta plus c. Now, sine of 2 theta, just to pretty this thing up a little bit, this is going to turn into 2 theta plus 2 sine theta cos theta plus c. Now you may say, but Ripley, we have a massive problem here. I started with x's, and now you have this thing in terms of theta, and I don't even know what kind of voodoo nastiness you did to get us out of the x and into the theta. It wasn't a typical U substitution. I'm going to show you something. This is really cool. Follow the ugly green arrow. Do you agree that this can be written as x halves is equal to sine of theta? Hopefully you do, because it's true. Which means there exists a right triangle such that if I had an angle here called theta, I could put it up here if I wanted to, but I like it in the bottom left. It makes me happy. The sine of theta is x over 2, right? Opposite over hypotenuse. So this guy has got to be, with a quick and easy down and dirty little Pythagorean theorem, what the heck? Wait a sec. So wherever I see a sine of theta, I know that, wait, okay, I've got this triangle, this right triangle that came out of this whole, that's why it's called trigonometric substitution. Not only do I substitute trig stuff, but I get to use this triangle. Now I'm going to show you something. This is always true of a trig substitution integral. That you will always end up with your integrand somewhere on your triangle every time you do a trig sub. Every single time. No doubt about it. Now I'm going to finish with the ugly green. We have a bit of a problem here. There's no fancy way that I can get rid of this theta except to use the inverse sign of x halves. I am stuck because that's what theta is. It doesn't have a choice by virtue of the way in which we defined it. However, watch this. I know that this 2 sine theta cos theta is going to turn into 2 times, well, sine theta is x halves, times cosine of theta. Well, cosine of theta is adjacent over hypotenuse, which is the square root of 4 minus x squared over 2, and then plus c. Cancel, cancel, and I end up with the inverse sine of x halves plus x times the square root of 4 minus x squared all over 2 plus c. Probably not your first guess, was it? Now, this form, the reason that I knew to do this is because this integrand was of the form the square root of a squared minus x squared. Now, when you have this form, what you want to do is let x equal a sine of theta, because all this beautifulness comes popping out. Now, there are 2 other forms that we have to respect. The other form is x squared minus a squared. But look close over here. Do you agree that tan squared of x is equal to secant squared x minus 1? Now, I have an a squared here. However, if I let x equal a secant theta, then watch what happens. This turns into the square root of a squared secant squared theta minus a squared, which turns into, notice I can factor out the a squared, so I will get a times the square root of secant squared theta minus 1. The whole thing turns into a tan theta. That's some magic right there. Well, what's the other one that I'm missing? Look close. I've got an a squared minus x squared. I've got an x squared minus a squared. Hey, guess what I'm missing? I'm missing an x squared plus a squared. Well, look at your Pythagorean identities and see if you can figure out what it is. Well, if I let x equal a tan of theta, well, let's see what would happen. This will turn into the square root of a squared tan squared theta plus a squared. I can factor out my a, and I end up with the square root of tan squared theta plus 1, which is a c. Well, hush my mouth. That is magic. Now, let me be clear. Remember back in integration by parts when I hooted and hollered and waved my hands and said, don't freaking use this technique unless you absolutely have to. Take that sentiment and square it with trigonometric substitution. Trigonometric substitution is awful. There's 1,000,006 different ways to get lost in the middle of your work. And I'm not going to leave you hanging. We're going to do a few problems. We're going to do a couple of juicy ones that are super fun to do. But I want to be incredibly clear. If I don't have to use it, don't use it. If, for example, I have x times the square root of 4 minus x squared, right? Let's say I got that guy. And you're like, oh, Ripley, I have a new tool. Let's use it. You just handed me the most esoteric, crazy tool I've ever seen in my entire life. Well, let's hold back a sec. Do you notice that the derivative of x squared is very close to x? So I can simply let u equal 4 minus x squared. Du is equal to negative 2x dx. I don't want a negative 2x dx. I want an x dx. So I do negative du over 2 is equal to x dx. And look at what happens. This becomes negative 1/2 the integral of the square root of u du, which I know turns into negative 1/2 times 2/3 u to the 3/2 plus c. No trig sub necessary. I end up with negative 1/3 4 minus x squared to the 3/2 plus c, and I'm done. I do not want to use this if I don't have to. But when I do have to use it, it's a really darn good trick. Okay? All right, I'm going to do a problem for you because these to me are super fun. What if I were to throw this problem at you? Let's do dx over, and I'm going to do, let's go, no, I don't want to do that one. Let's do one that's more fun. Let's do, how about the square root of x squared minus 4 over x dx? Because this is a little confusing, isn't it? This is just a little bit crazy because this smells like a u substitution. This is a nasty trap. Excuse me, I'm going to take a quick drink of water. But the problem is if I let u equal x squared minus 4, when I take the derivative, I end up with a 2x. I don't want a 2x dx. I want a dx over x. Crud. Guess what? I got to use a u substitution. The question is, which one? Well, let's double back and see what happens. Okay, I have a squared minus x squared minus a squared, x squared plus a squared. So I've got x squared minus, okay, this is an a squared minus x squared. And that told me, let's go back one more time, to use a secant theta. So I'm going to let, here we go, I'm going to let x equal 2 secant theta, whoops, secant theta, right? That's it. That's all I'm doing. We'll set the whole thing up here in just one sec. dx, I need to account for that one. That x is going to be 2 secant theta. So this becomes dx is what? Well, 2 secant theta tan theta. So I've got this accounted for. Now let's go through the drudgery of accounting for all this. I'll change colors so you can see that this is a big step. First things first, I know that I'm going to end up with the square root of 4 secant squared theta minus 4. Underneath is going to be a secant theta, and then times secant theta tangent theta. You know what I forgot, you guys? You got to yell at me. There's a d theta, and there it is. I know you guys were putting pencil to paper and saying, I'm going to tell Ripley, screwed up. That's valid. Okay, we'll get rid of that guy. Okay, now let's see what happens. Well, I can factor out a 4. So factor out a 4, take the square root of that, and I end up with 2. And I end up with, let's change colors again. Let's do it purple. Underneath here, I end up with 2 square roots of secant squared theta minus 1. So this guy just turns into 2 tangent theta, doesn't it? Because this secant squared minus 1 is tan squared. The square root of tan squared is tan theta. So watch what happens. Let's go back to my blue. This turns into 2 times, I don't know what happened there, 2 times the integral. Whoa, that was cool. 2 times the integral, sorry everybody, of tan squared theta d theta. And what do we know the antiderivative of tan squared is? Again, everything we do so that we can distill it into a form that we know the antiderivative of. This just turns into 2 secant theta plus c. Derivative of secant is tan squared, right? That's not right. Let's try that again. Bear with me for just a sec. It's getting a little late. I'm doing this video late at night. Let's try that again. I'm going to do one more trick because I don't want to take the antiderivative of tan squared. The derivative of tan is secant squared. The derivative of secant is secant theta tan theta. But I do know that this becomes 2 times the integral of secant squared theta. That's where I want to be, minus 1 d theta. What a moron. This turns into 2 tan theta minus 2 theta plus c. Isn't that nice? Now, here we are again. We let this x equal 2 secant theta, which implies that secant of theta is equal to x halves. Now I have to account for this silly theta here. So I know that theta is equal to the inverse secant, which is ugly. We know there's another way to write that. I could write it as the inverse cos of 2 over x, but we're not going to do that. We're going to write this as the inverse secant of x halves, if you remember that from pre-calc. So this theta is now taken care of. However, watch, I can build a sweet triangle. It's good to see your professors make stupid errors from time to time. Here's a theta. All right, how's secant theta work again? Oh, yeah, right. It's 1 over cos. And cos is adjacent over hypotenuse, so we're going to do hypotenuse over adjacent, right? So this is going to be x over 2. And what's this guy become? Well, the square root, just like we said, x squared minus 4. Remember what I said before? This term always shows up on my triangle. Now, why is that important? Well, look close. We've gotten the theta taken care of. Now I need to take care of the tangent. Well, TOA, opposite over adjacent, I've got the 2's. This is those two, that 2 and that 2 are going to cancel. So I'll end up with 2 times the square root of x squared minus 4 over 2. Goodbye. Isn't that beautiful? Minus 2 inverse secant of x halves plus c. Isn't that gorgeous? I want to clean it up. Square root of x squared minus 4 minus 2 inverse. Oops. Inverse secant of x halves plus c. And I'm done. Happy, happy, joy, joy. Look, this is confusing. I get it. I am not expecting any of you to walk into my classroom after having watched, I don't know, a 20-minute video on trigonometric substitution and be masters at it. We're going to spend time in class, or we're going to take our time in class. So don't panic. We'll see you in class. We'll do some problems. Have a wonderful day, and I'll see you tomorrow.